Hello everyone, welcome to 4th lab of digital signal processing. My name is A. Sai Madhav. In this experiment, what we'll be learning is about DFT, discrete Fourier transform. So basically, what is the aim of this experiment? In this experiment, we try to find the magnitude spectrum of the signal which is sampled at 100 Hz using discrete Fourier transform algorithm. And what we do is, after finding the magnitude spectrum, we calculate its frequency and compare it with the frequency we find through autocorrelation. Okay, so basically a discrete Fourier transform, what it does is we take a discrete signal which is finite, and we multiply it with e power I minus I 2 pi by capital N into kn. So this is basically the formula which is written right here. So what we do is, we after finding the discrete Fourier transform, we get both the magnitude and phase spectrum. But in this experiment, I'm going to mainly focus on the magnitude spectrum because that's what helps us in finding the frequency of that signal. Okay, so moving on to the DFT matrix. DFT matrix is just an expression. Now in the previous slide we have seen that this equation e power minus I 2 pi by capital N into kn. So what exactly k and n depend on? See, n depends on the length of the signal what we are taking, and k also basically depends on the output what we get. And if we generally this is a generalized equation for an n-point DFT matrix, and the same goes here with the DFT matrix. What we do is 1 by root n into omega. Here the symbol omega which is written here, which is basically e power minus I 2 pi by capital N. N is the length of the DFT matrix. Order is n by n. So n is the order of the DFT we are applying. Like if it's like it will be a second order DFT, third order DFT, fourth order DFT. So based on that, the omega value changes here. So we can clearly see it's omega square, omega cube. So what it takes is, it varies along horizontally in terms of k and vertically in terms of n. So it's or the other way. So when we take this discrete signal in term of n by 1 matrix, 1 by n matrix, and the DFT matrix is n by n, the output will obviously be a 1 by n matrix, which will be the Fourier transform of the given signal. So before I show these results, I'll just go to the Arduino coding and I'll show you what exactly I have written. Okay, in this experiment I have taken the signal, so like I get number of samples as 75. I've taken the length, I have defined two matrices, and these are just the basic definitions, like initializations I give. Now what I do is, I've initialized the sum and I've initialized the count. Now what I do is, I'll just sum up all the values and finding the number of non-zero values, and I just average them. It's like just finding the mean of that. And now what I do is, I've taken two different numbers. See, the problem in Arduino is I cannot directly define the complex number. So what I did is, I've divided it into cos and real and imaginary part. So the real part has cos theta and the imaginary part has minus j sin theta, because the formula which I have shown, e power minus j, so I have to get minus sign there. Now what I do is, I multiply the signal with the corresponding value. Like I am varying it both row wise and column wise. So first fixing the column, I'll fixing the row, I'll take the different column values and it keeps on adding it. So that's what this formula shows. Sum 1 is equal to sum 1 plus p of j into y of ij. So it's like, suppose y of 0 0, y of 0 1, 0 2 up to 0 n minus 1. It will take all the horizontal component addition, vertical component additions, because see, this 1 by n into n by 1 by 1, so it will take the first value. So that's how I calculate the real matrix and the imaginary matrix. Now what I do is, I'll find the magnitude. I have to find the magnitude spectrum. So that means I have the real part, imaginary part. So the output which I have to get is square root of real square plus imaginary part square. That will give me the magnitude spectrum. So here Now I have found the magnitude spectrum. Now I want to plot it. Okay, so this I have intended to test the code. Okay, now I am sending it into the Arduino board. So opening the serial plotter. See, I mean, like, I've already written the code twice, so let me just comment it again. Just give me a second. So now I'm uploading this and when I open it, I have to find the spectrum which I've already seen before. It showed double 2 times, but the pattern is like of a higher by a higher magnitude. If it shows at a certain frequency, that means that is the dominating frequency component in the signal. So you can see the parts here. These are the dominating frequency parts. It shows two different type of frequencies, but we consider the first peak we get. That helps us in evaluating the frequency. Okay, so now what I do is I'll print the. I have also written the autocorrelation function. I'll show you that also. Okay, so now what I did is first I have to find the autocorrelation function, right? So it is a function of delay. So I've defined a function r of 75 because it will be of length 75. So I've initialized it from like 0 to length. I have to take it, and this is the function which I get autocorrelation, which I've already shown in my previous experiments. And now what I do is I'll plot this and show you. I'll comment the previous ones just to avoid any, like confusion. And so the first peak is not that clearly visible. So what I'll do is I'll run this loop again. So the only reason I'm running this loop again is because till now I wrote it in a void setup, so it will run only once. As I explained in the first video, I've shown that if I run it in void setup, it will run only once. If I keep it in loop, it keeps on running. See, this is my peak and it keeps decreasing. Okay, so now you understood, right? This peak is like my first peak, and now I have to find the zero crossing points. So for that what I do is, okay, let me just remove this while loop. So now what I do is I have to find the point where it first crosses the zero. Like the previous value should be greater than 0 and the next value is less than 0. In that case, I'll directly find the zero crossing point. So after finding the zero crossing point, I have to find the peak that comes after the zero crossing point. So the reason why I'm doing this is the property of autocorrelation function is that the period of the autocorrelation function is same as the period of the signal. So if I find the period of this autocorrelation function, I can directly calculate the period of the signal using this function. So I've found the maximum, and now what I do is I've written this formula because I've sampled it. I've known how to I have the formula for calculating the autocorrelation function. And okay, so now what I'll do is let me compare these. Okay, so I will comment these two because I don't want any. Okay, so let me just run this code so that I've changed, because I've made some changes. Now what I have to see is it must be nearly the same. The function which I've calculated, the value which I've calculated through autocorrelation function or through the DFT metric, I should not get any much of a difference. So okay, those were the previous values which I have running. So now we can see the frequency value is 70, which I have calculated through DFT, and this is 71.43 through autocorrelation function. Now I have already calculated the error, which I'll show it in the presentation, and these are the results. Using DFT matrix, the frequency I got is 70. Using autocorrelation function, 71.43. So now the error is 2.0428, which is pretty small. So we can clearly see that the error is very small, and I can even minimize this error by taking more number of samples. The problem which I've got is in Arduino, I'll be taking if I take 150 samples, I mean if I sample it with a higher rate, I will get more number of samples, and the DFT matrix becomes very large so that the board cannot store it. That's the only reason I've tried to take it to 75. Okay, so now you can observe that if I had taken more number of samples, my frequency calculation using DFT matrix would have been much more accurate. So that's the end of the experiment. Thank you for watching the video.